Hello, my name is Yusuf Renesis. We start this course with section 1.1 called Functions. You can see the objectives. We will define a function, or we are going to talk about function notation. We're going to evaluate functions, and then finally we're going to describe the domain and range of a function. So you might be wondering, what is a function? And in math, basically a function is like a machine that takes in a number and it returns exactly one number. The number we plug in is called the input, and the number that we get out is typically called the output of the function. Some examples of functions include the following: y equal to 2x plus 3. This is known as a linear function because the x has power 1, even though it's not written, we understand it's there. We can also call this f of x. So we can use the name f to refer to this function, and then the x right inside the parentheses will be typically known as the independent variable. So the dependent variable will be y or f, and in this case, the independent variable would be x. There are a couple other examples right there on the page for you. Y equal to 3x squared minus 4 is known as a quadratic function. The name quadratic refers to the fact that we have a power 2 in this x variable. And then finally, we have the definition of exponential functions, which basically implies that there's a base. In this case, we're using the letter e or the value 2.7 to be in the base. That's why this example is known as an exponential function. So as we mentioned, the number that you plug in is called the input or the independent variable, and the number you get out after evaluating the function is called the output or the dependent variable. So we're going to give some examples on how to evaluate functions. So in this case, we're told given f of x equal to negative x squared plus 3x plus 1, we are supposed to evaluate f of negative 2. So what exactly is this problem asking us to do? It's very simple. We are expecting to see an x right here, but instead of an x, we see a negative 2. So what we're going to do is take the function f of x, and every time we see the x variable, we're going to replace it with the value that is being provided by the problem. In this case, the value is negative 2. So there used to be an x inside the parentheses here, and I'm putting parentheses where the x's used to go, so we can keep track of everything. And also it's a good idea because we have a negative 2 that we're going to evaluate in this example. So setting up the problem, I get negative parentheses negative 2 squared plus 3 times negative 2 plus 1. And now it's just a matter of evaluating the function by using the PEMDAS operations. So I'm going to start with the powers. Negative 2 squared is going to be 4, and I'm just going to copy the negative in front of it. 3 times negative 2 is going to be negative 6, and there's a plus 1 at the end. Just leave it alone for now. And finally, negative 4, negative 6, and plus 1. When you add all that up, the outcome should be a negative 9. So this is the answer in this case after we evaluate the function f at negative 2. So the input in this case is going to be the value negative 2. So that's the input. And the output in this problem is negative 9. Sometimes we like to write this as an ordered pair. So sometimes you'll see something like negative 2, comma, negative 9 written down. This is in alphabetical order. X is going to go first, and Y is going to be second. So in the part 2 of the problem, we are asked to find f of a, or evaluate f of a. The function is still the same. So again, I'm expecting to see x, but I'm seeing a different variable in this case. I'm seeing a. So I'm just going to go as before, replace all the x's in the original problem with the letter or the variable that I see in this case, which is a. So I'm going to plug in the a into all the places where x used to belong. And this is straightforward. There's not much to do here. I'm just going to write negative a squared plus 3 times a plus 1. And since none of these terms are like terms, this is where the problem ends. Moving on to the next part, it says f of 2b. As usual, I'm going to replace the x with 2b. And as before, we're going to leave some spaces where the x used to go. I'm going to put parentheses there just so I can remember where the x used to be. And I'm going to replace the x value with the number, or in this case, the quantity, 2b. So if I plug in 2b into all the x's, I'm going to end up with negative 2b in parentheses squared plus 3 times 2b plus 1. And as usual, PEMDAS takes over. 2b has to be squared first. That's going to give us 4b squared. The minus comes down in front. 3 times 2b is going to be 6b. And then finally, there's a +1 at the end. And again, there are no like terms because the b's in this case have different powers. They cannot be added. The 1 doesn't even have a b, so we cannot add anything. So this is it. We are done. This is the final answer. And now we come to the last part of this problem where we have to evaluate f of x plus h. Again, it's just slightly more complicated because we have x plus h rather than x, but the process is the same as before. We plug the x plus h in all the places we used to see an x. The tricky part is evaluating this x plus h squared. So, if you don't know how to do this, you could just go to a scratch paper and write it twice in a row and just FOIL it out. X times x is going to be x squared. X times h is going to be xh. And then h times x is going to be xh again. Finally, h times h is going to be h squared. And these two guys in the middle are like terms, so we can combine them, and this will be x squared plus 2xh plus h squared. So we know that that answer goes in front, but be careful because there's a minus in front of it. So to keep track of everything, I'm going to put minus, I'm going to put a little bracket there and just copy the solution that I got, which is x squared plus 2xh plus h squared. And the rest of it should be pretty straightforward, pretty simple. We'll just multiply out the 3x and the 3h. So that's going to be next. And finally, there's the +1. It remains to just FOIL this minus sign out. We just need to get rid of it. So we'll just distribute it basically to everybody inside the bracket. And so the result will be negative x squared minus 2xh plus h squared. And then 3x, 3h plus 1. They're just basically going for the ride. They have nothing to do at this point. We just copy them down. And a quick check to see if we have any like terms. It doesn't appear that we have any like terms. This term has x and h. This one has only x. This one has only h. So we cannot add those with each other. This one has x squared. This one has h squared. They cannot be added with each other. So we can just end the problem there. This is it. That's the answer. For example 2, we're basically provided with a few different functions. And again, the question is asking us to evaluate each function. Evaluate just means plug the number in and see what you get for the result, for the output. And in this first part, the g of x is the function called the square root of x minus 1. And we're supposed to evaluate it when x is equal to 10. So as before, I'm going to write g of x equal to the square root of x minus 10. Sorry, x minus 1 rather. But in place of all the x's that used to be there, I'm going to leave some gaps, some spaces, and write down the number that I'm provided with. In this case, it's a 10. And again, PEMDAS tells me that I'm supposed to subtract 10 minus 1 first, and that gives me 9. Finally, the square root of 9 is going to be 3. So this implies that g of 10 is equal to 3. Case is 10, and the output is 3 for this function g. Next, we have the function m, which is called m of x equal to x over x plus 2. So this is an example of what we call in math a rational expression. It's called a rational expression because we have a fraction with x on the numerator and x on the denominator. So as before, it tells me to put mx equal to x over x plus 2. So I'm going to leave some spaces, some gaps where the x used to be. I'll put parentheses there just to remind me that this used to be where the letter x used to be found. And in this particular case, I'm supposed to replace it with 2. So when I do that, I'm going to end up with 2 divided by 2 plus 2, which is 4. Or just simply 2 over 4 is 1/2. Okay. And so m of 2 is equal to 1/2. So the input was 2, the output was 1/2. Notice how we always get one single output. This is why we call these things functions. For m of x next, it's the same function as before, but we're using a different value to evaluate. In this problem, we're going to plug -2 in. So it's a little bit strange because what will happen, we will end up with a -2 plus 2 in the denominator, and maybe you remember this, maybe you don't, but we're going to get -2 over 0, which is what we call in math undefined. You cannot divide by 0 in math. Undefined. Or another way of saying this, we can say no solution here. There is no answer because it's -2/0. The problem does not have a solution. I will leave example 3 as practice for you, and I will write the solution in a separate PDF that you can find in this course shell. So give it a try. The function in this case is called NFT, and you're expected to plug in 4. So this is an example of a type of application where n in this particular problem, the function n, is the number of cars produced at a certain factory, and so on and so forth. So give it a shot and see if you can get this one done on your own, and then confirm your result by looking at the PDF with all the solutions.
The last thing we'll talk about in this section is the definition of the word domain and range for functions. The definition is straightforward. For a function, the domain is the set of all the input values for which the function is defined. In other terms, it's all the numbers that you can plug into the function in order to receive a real number as an answer. So for instance, on the previous page, we had an example where m of x was x over x plus 2. We tried to plug in -2 into that function, and unfortunately, we got a no solution. So the conclusion would be that the domain of this function m of x should not include the number -2. It would be basically every other real number except for -2. And so the range of the function, which is the second term that we have to define, is the set of all the output values. Basically, it's every number that you would get when you plug in all the legal values. That's what we call range. And in math, we are expected to be able to write the domain and range in different ways. Sometimes we're asked to find the domain and write it in interval notation. Sometimes we're asked to find it and write it in set builder notation. So what we're going to do in example 4 is practice both of those types of notation. So all we're doing here is just taking this sentence that's being provided and writing it either in interval or in set builder. So the first part, it says x can be any number that is greater than 4. And we are expected to write it in interval notation and in set builder notation. So I'll just do both, starting with interval notation first. Since x could be any number bigger than 4, if I imagine all the numbers being placed on the real number line with kind of plus infinity on the right side, negative infinity on the other side, and 4 somewhere here, the sentence x can be any number that is greater than 4 would imply that x could live anywhere here. It could be 5, it could be 6, it could be 7, or anything bigger than that. However, it cannot be 4 itself because it must be strictly greater than 4. So to refer to the fact that it cannot be equal to 4, we usually write parentheses on the number line, or sometimes some people would like to put an open circle where the 4 is. So either parentheses or open circle, depending on your preference, would imply the same thing. I prefer the parentheses notation because then I can copy that same notation to my interval notation and write the start of the interval, which is in this case 4, and the end of the interval. Since this interval goes on forever, there is no end, so we just write plus infinity. And infinity is always going to have parentheses next to it. Whether it's on the left or right, it doesn't matter. We always put parentheses there. So this means don't include 4, parentheses with 4 next to it means do not include 4 in the interval. And the end is going to be basically infinity. So start and the end of the interval. So that's the end. That's basically it for interval notation. For set builder notation, it's a little bit different. We're going to use curly braces at the beginning and curly braces at the end. So this indicates that we're dealing with a set. And what's a set in math? It's basically a collection of things. In this case, we're dealing with numbers, so it's a collection of numbers. And because we're describing that x is any number that is greater than 4, we're going to write x first, referring to the variable we're working with. We also write a little vertical line, basically saying x under the condition of or such that. This is what that line means. Basically, it's the condition of what x needs to satisfy. So the variable is x, and it needs to satisfy the inequality that x is bigger than 4. So my inequality does not have an equal sign because x must be strictly greater than 4. It cannot be equal to 4. Okay, that's the answer for part 1 of the problem. So we've got two solutions. We've got the interval notation first, and we've got the set builder notation next. So let's try to do part 2 of this problem in the same way. It says y can be any value less than or equal to 5. So again, a helpful visual diagram would be to draw a number line which represents all the numbers in the world and put plus infinity on one side, minus infinity on the other side. And somewhere along the way, we're going to find the number 5. And y can be any number less than or equal to 5. So the key word here is that the y can be less than or equal to the number 5. So thinking of some numbers that are smaller than or equal to 5, I can think of 4, 3, 2, 1, -10, and so on. These are all these numbers on the left-hand side of 5. Now, because y can be equal to 5 in this case, we are going to use a bracket, or some people prefer to write a solid circle at 5. Personally, I like the bracket notation, again, because it's helpful when I have to translate this picture into interval notation. So in interval notation, I would write something like -infinity, which is the start of the interval. I'm always starting from the left and going to the right. So -infinity goes first, and 5 is at the end of the interval, or the last number. Infinity always gets parentheses, whether it's positive or negative, so I'm putting parentheses there, and then 5 is going to be bracketed, and the bracket indicates that 5 is allowed as a value for, in this case, y. The set builder notation is next. So in set builder notation, again, we're going to write these curly braces. The variable we're working with is y, so we put y first, and as before, we put the little slash symbol, or y such that, or under the condition of. That's what that symbol means in math. It's just basically a way of saying that's the condition that y needs to satisfy. So y needs to satisfy the fact that y has to be less than or equal to 5. It could be less than 5, or it could be equal to 5. And again, that's the end of this particular part of the problem. So it's two solutions because they ask for two different things. Finally, the last part of the problem says t can be any value between, but not including, 0 and 10. As usual, I like to draw my diagram, and here's my real number line with infinity on one side and -infinity on the other side. So plus infinity and minus infinity. Along the way, I'm going to come across the number 0, and I'm going to see the number 10. Don't worry about putting every little notch in the middle, because then you're going to have to worry about spacing. Did you put the appropriate number and so on? We don't need to worry about all that. We just want to see 0 and 10 because these are the relevant numbers. And in this particular problem, we're working with t, and t can be any number between 0 and 10. So I'm thinking something like 1, 1.3, maybe 4, maybe 4.7, and so on and so forth. So this is the part of the graph that we care about, and we're told not to include 0 or 10. So as before, not including means put some parentheses here and put some parentheses at the 10. So in interval notation, this would be 0, 10 with parentheses on both sides. And in set builder notation, the curly brace and the other curly brace, we're going to put -infinity, we're going to put t in this case because that's the variable we're working with, such that the t has to live between 0 and 10. So t is any number between 0 and 10. Straightforward. 0 must be smaller than t, which in turn must be smaller than 10. Okay, so that's the end of problem 4, or example 4. Last thing we need to do is to be able to determine the function's domain if the function is given to us. So that's a little bit tricky, and with experience, you're going to be able to do this in no time. But the idea is to always assume that the domain of every function is all the real numbers, and then see if you need to remove some of them. So for example, if you have a square root function, Then you can't have negative values, so you need to remove those. If there's a fraction, the denominator can't be 0, so figure out what numbers make the denominator 0 and remove those. On the other hand, if you want to find the range, at this point in time, the most easiest option for you is to just graph the function on your calculator and look at the graph and decide off the graph what are the values of y's that you see on the graph. And depending on the function, it could be all real numbers or a subset of those. So given the function f of x equal to 5x, we're looking to find the domain and range of this function. So this is what we call a linear function because x has power 1. Linear functions, basically, when you draw them, they look like a straight line. So if this is the xy plane and I want to draw the function, I'm expecting to see something along this graph. So it's going to pass through the origin. It's going to be slanted upwards as I go from left to right. And so the domain of this function f of x is going to be all the real numbers. These are all the x values that can be found in the world. There are no restrictions on this function. So in interval notation, I can write negative infinity, comma, infinity. So that's my domain. And for the range, as usual, looking at the graph, I don't see any gaps. The line basically covers the full y-axis, so the range in this case is going to be negative infinity to infinity. And again, I'm using interval notation to describe the answer. So it's a good idea to remember that linear function, except special lines like horizontal ones or vertical ones, the domain and range for every linear function, except for those two I just mentioned, is going to be always negative infinity, comma, infinity. So linear functions, straightforward. The only exception, as I mentioned, is the horizontal lines or vertical lines. Those will have special domain and range. Part 2 gives us the function f of x equal to 1 over x minus 2, and this one is a fraction. So we have to be careful. This fraction cannot have a 0 on the denominator. So the question is, what would make x minus 2 equal to 0? Because if we got a 0 for some reason, then 1 over 0 would become undefined or no solution. And in this particular instant, the number would be 2. So the number 2 is basically a bad value. We cannot have it because if we did end up plugging 2 into the function, we end up with 1 over 0, which becomes undefined. So for the function, the domain is going to be everything except for 2. So how do I say that? So there are two different ways. If I'm using set builder notation, I can say take every x you like, except the function that doesn't except the x value 2. The function doesn't like that one. So I can say something like x such that x is not equal to 2. So that's using set builder notation. But if I want to write it in interval notation, I could write something like negative infinity, comma 2, and then 2, comma infinity, with infinities always getting parentheses. 2 is not allowed, so I put parentheses, and then I put the union sign in the middle. So in other terms, the interval that I'm describing is all the numbers in the universe except for the number 2. So I can have every number before, every number after. I cannot have 2 itself. So this interval notation translated would be that solution. So that's going to be my domain. And for the range, it's going to be a little bit more difficult. So we'll have to use a calculator. So let me turn it on and show you the. Okay, so here we go. My calculator, I'm using the TI-84 Plus. Yours might look a little bit different, but I'll try to show you the steps. First, we're going to need to turn it on. Then we're going to click on the top left corner where it says y equal to, and this gets us into the y menu. We have different letters here that we can use for the name of our function. So I'm going to call my function y1. And the problem asks me for the domain and range of 1 over x minus 2. So I'm just going to type in 1 divided by, and because my denominator has multiple variables and I want everybody to be in the denominator next, I'm going to put parentheses and then x minus 2 and close the parentheses. So this is going to graph the function that we're given. If I click on zoom next, there are different options. I can zoom in, zoom out, and so on and so forth. I'm going to pick the standard zoom, which is option number 9. So you can either click down multiple times with the arrow key, or just click the number 9 and it will take you to the graph. And this is what the graph looks like. So in this particular instant, it seems like the graph is going to get closer and closer to the x-axis on the left and right hand side, but it will actually never touch the x-axis. So this implies that my range is going to be all the real numbers except for 0. So I can write it in interval notation as such. Negative infinity comma 0, union 0 comma infinity. So this is going to be interval notation. Or if I want to use set builder notation, I can write something like curly brace. The range describes the y value, so I'm going to put y such that y cannot be 0. And either way, it's up to you. You can decide whether you like interval notation or set builder notation. Either one is acceptable. So again, this one is the set builder notation. This one is the interval notation. This is again interval notation. And finally, we have the function f of x, which is the square root of x, and we're expected to find the domain and the range. As I mentioned earlier, the square root function doesn't like having negative numbers inside. So for example, if I ask for the square root of negative 4, you should say no real answer. I mean, there is a complex number or an imaginary answer, but we are not interested in those yet. The domain is only interested in real numbers. So the function f of x in this case cannot have a negative value inside for the value x. So in other terms, if I imagine the whole real number to represent every x in the universe from negative infinity to positive infinity and 0 somewhere along the middle, then x cannot be any of the negative values. Can only be 0 or something bigger than 0. 0 is allowed because the square root of 0 is in fact equal to 0. So this is a legit value. So the domain, and again, you can decide whether you like set builder notation or interval notation. I'll write both, and you can decide which one you prefer in this case. So x for the domain such that x must be bigger than or equal to 0. So I'm using the inequality with the greater than or equal to 0. This is the set builder notation. And if I want to write it in interval notation, I'm going to write 0 comma infinity, with infinity having parentheses, with the 0 having a bracket. So sometimes one of them is slightly simpler or slightly faster than the other one, but it does not matter regardless of which one you pick. Both are acceptable solutions. Sometimes the problem or the software asks for a specific type, so just pay attention to that. On the other hand, the range, again, if you don't know this already, your best option would be to graph the function f of x, which is the square root of x. Okay, to graph the function, we are going to turn on our calculator again, and we'll use the square root symbol, which is the same key as x squared, but sometimes it's in yellow or blue, depending on your TI calculator model. So you'll have to click the second key first before you click that square root or the x squared key. And in this case, I'm going to plug in x squared. Sorry. I'm supposed to graph square root of x only. Okay, here we go. The graph is going to determine that the range starts somewhere at 0 and it goes on forever. So I'm looking for the corresponding y values. Basically, this graph, no matter how much you zoom out, it's just going to keep climbing up towards the right-hand side of the page. So in this particular instant, the domain is going to be 0 to infinity, and the range is going to match it. So the range is going to be 0 to infinity, with 0 being allowed as a possible answer, because obviously when I plug in 0, I get 0 back, and that's the number that shows up in my range. So this is the interval notation, and I'm not going to write set builder notation because it's literally the same as what we previously mentioned. So there it is. Pick one of those, and that's it for this section. See you in the next one.